going to be talking about the global climatic and ecological responses to medium-sized or kilometer-sized asteroid collisions with Earth. So, asteroid impact is a fundamental process in our solar system, and this map shows the distribution of roughly 200 confirmed terrestrial impact craters on Earth. And one of the largest impact crater is the Chicxulub in Mexico, and this roughly 200 kilometers wide crater was hit by the impact of massive asteroid about 10 kilometers size 66 million years ago. And this impact event has been found to be the main cause for the mass extinction event of the Cretaceous-Paleogene boundary. And it may cause the extinction of 75% of all species on Earth, including all land avian dinosaurs. Asteroid impacts are much less frequent today, but there are still many near-Earth asteroids in our solar system, and they are defined as small rocky bodies with nearest distance to Sun less than 1.3 astronomical unit. Starting from the 1980s, NASA has discovered more than 36,000 near-Earth asteroids, and their sizes range from a few meters to several hundred kilometers. And among them, more than 4,900 are medium-sized near-Earth asteroids with diameter between 300 meters to 100 meters. And this abundant medium-sized asteroids still pose threats to our planet. So, according to the observations and the statistical analysis, the medium-sized asteroids about 1 kilometer in diameter are estimated to strike Earth every 600,000 to 700,000 years. Impact probability is extremely low, but it's still possible that one medium-sized asteroid will collide with Earth within the next 2 centuries. For example, the asteroid Bennu, one of the dangerous asteroids, it has a diameter about 500 meters, and it's predicted to hit Earth in the year 2182 with a chance of 1 in 2700. Just for your reference, this chance is higher than the likelihood of dying in a bicycle accident. And if such a kilometer-sized asteroid hits the land surface, and it will cause dramatic climate effects because the impact cratering process will emit huge amounts of aerosols and gases into the upper atmosphere. So there are 3 main groups of fine particles that have climatic substantial impacts on climate, including the nanometer-sized dust particles, sulfur, and soot. In our study, we mainly focus on the dust nanoparticles because it accounts for a large fraction of the total ejecta. And these dust nanoparticles are formed by the condensation of the rock vapor in the impact plume or fireball. So we want to address the question that how will the massive dust injections from kilometer-sized asteroid collisions affect Earth's climate, vegetation, and marine productivity. So to simulate the climate effects of dust particles from asteroid impacts on land, we apply an idealized horizontal and vertical distribution as input into the Earth system model. we use the fully coupled high-top community Earth system model CSM2 with vacuum 6 with interactive chemistry as well as land and ocean biogeochemistry. And we conduct a set of idealized dust perturbation experiments and pre-industrial and present-day conditions. So we mainly focus on 4 dust scenarios with total amounts of dust of 100, 200, 300, and 400 million tons. And these 4 dust scenarios correspond to the impact of asteroids with diameter between 450 to 750 meters. Next, I would like to introduce our model simulation results of 4 dust scenarios. So left panel shows the global total dust burden and the aerosol optical depths over 48 months after impact, or 4 years after impact. So after initially injected on January 1st and in the upper stratosphere, the dust particles gradually settle out of the atmosphere. And after 2 years, 90% of total dust is deposited to surface. And the pattern on the right shows that dust particles are quickly dispersed around the globe by the Abrupt circulation in the stratosphere after initially injected in the Western Hemisphere. Then let's take a look at the physical responses of the climate system to dust perturbations. Here we show the surface shortwave flux, surface temperature, and precipitation anomalies relative to the control simulation for 48 months after the impact. So the global distributed dust layer block sunlight and cause widespread reductions in shortwave radiation. And global surface temperatures show rapid and strong cooling with the maximum decrease of -4 degrees Celsius. And this cooling is comparable to the cooling estimated for the Toba super eruption 74,000 years ago. And surface temperature creates more over land than over ocean, especially in the northern hemisphere due to the faster response of land. And we also find the weakened hydrological cycle with precipitation decreased from 5% to 15% in 3 years after impact. And the precipitation pattern suggests the weakening and equator shift of the ITCZ and SPCZ. And we also find strong chemical responses of ozone in the stratosphere. So the total column ozone concentrations here show dramatic decrease for 2 years after the impact, and the maximum ozone loss reached 30%. The substantial ozone depletion occurs over middle to high latitudes in both hemispheres in the upper stratosphere, and this is caused by the extreme warming of up to 100 K due to the radiation absorption by dust particles. The abrupt impact winter can cause serious disruptions of photosynthesis in terrestrial and marine ecosystems. Here we show the net primary productive NPP on land and in the ocean. We can see not reductions in land NPP lasting for 19 months after impact, and the negative anomalies mainly occurred over the middle to high latitudes in the northern hemisphere and the tropical West Africa. However, the marine MPP only shows a short period of decline for 5 months. After that, the marine phytoplankton shows an early recovery and a quick rebound from the end of the first year. And this marine phytoplankton bloom is mainly caused by the iron-rich dust deposition into the ocean, because some asteroids can contain high abundance of iron, and that impacts induced dust deposition will add large amounts of iron into the ocean. So here we compare two simulations with different iron contents of 3.5 and 40% in the dust by weight. And here we can see that the marine phytoplankton bloom is dominated by the large delta blooms in the austral winter. And we found that these delta blooms mainly occur in iron-limited regions in the Southern Ocean and the Eastern Equatorial Pacific. So to conclude, we use the state-of-the-art Earth system model simulations to quantify the physical, chemical, and biological responses to different dust perturbations from medium-sized asteroids impacts on land. And our model simulations suggest that dramatic climate perturbations will last for up to 4 years after the impact, including strong global cooling, massive global droughts, and substantial ozone depletion. And the simulated reduction in the non-MPP would likely generate widespread food insecurity. But fortunately, the excessive phytoplankton blooms in marine biosphere after impact might help to alleviate the food crisis. So next, I will work with my colleagues to combine the simulated climate perturbations to our hominin and mammal models. We will explore how the abrupt events like asteroid impact will influence the habitats and the dispersal of hominins and mammals. Thank you for your attention.